Imagine a car driving around a banked track. This track forms a big circle, but the whole thing is inclined. We can see the car driving towards us. We'll draw a plan from the top. We have our large circle of radius r and our car driving around this way at some speed v. We can work out that the centripetal force required is Fc equals mv squared over r. We also know from previous work that there's a force down the ramp caused by gravity. So we have mg here, and we have the downslope equal to mg sine theta. This is going to be producing the inward acceleration in an ideal world. The car will be pushed down the track, and as a result, it will curve inwards. So can we work out the speed or the angle? Let's try looking at the reverse situation. Here's our track, and we know that it is exerting a force of mv squared over r on the vehicle. That means that the vehicle is exerting the same force on the track, mv squared over r. And so we know that part of that is going up the track, and part of that is going into the track. And we care about the up the track part. We've got our same right triangle as we did when we looked at downslope forces a long time ago, and we can see that therefore the upslope part of this is going to be mv squared over r times cos theta. F up equals mv squared cos theta over r. And our ideal situation is that F down equals F up, mg sine theta equals mv squared cos theta over r. And straight away we can see we can cancel out the m's. Let's divide both sides by g. Sine theta equals v squared cos theta over gr. We'll now move the cos theta across by dividing both sides. Sine theta on cos theta equals v squared over gr. And really importantly, sine theta on cos theta is equal to tan of theta. So we've got that the tan of the angle of the ramp will allow a vehicle to travel around with no net force sideways on the tyre when v squared is equal to g divided by and the radius of the corner. So let's look at an example. Tan theta equals v squared over gr. The Mercedes-Benz test track that you may have seen in videos has a radius of about 50 metres. And they tell us that the forces balance when the vehicle is travelling at about 150 kilometres an hour, or about 40 metres a second. We also know that g is equal to 9.8 metres per second squared. So what angle do we need? Well, tan theta equals v squared over gr equals 40 squared over 9.8 times 50, and that is equal to 3.26, and so theta equals 73 degrees. And so we need a very steep angle of 73 degrees, and our vehicle will be able to travel around this ramp at 150 kilometres an hour with no sideways force on the tyres.